Hello everyone here in the room, and greetings for the people following online. And welcome to the 2022 ECOM Seminar Series. And today is an honor and a pleasure for me to introduce Dr. Cathy Clerbaux and Dr. Sarah Safieddine. Sarah and Cathy are junior and senior CNRS scientists from Sorbonne University in Paris. After a postdoc at MIT, Sarah came back to LATMOS to work in the IASI team led by Cathy. Cathy is a PI for the IASI mission and an anchor affiliate scientist, and she's been working with ECOM since a while, she says to me. They're going to tell us about their studies on climate using the IASI satellite data. And I want to remember for the folks online that you can enter your questions in the space below the video. And at the end of the presentation, I will read those questions aloud to Sarah and Cathy. Please help me welcome them on the stage.
So, hi everyone. Thank you, Alessandro, for the introduction. So what I'm going to present here is the work of several people, and part of the team is located in LATMOS in Paris, and the other part of the team is located at ULB in Brussels. And I'll start, and then Sarah will continue. This is the IASI satellite instrument. It's like a cubical device. It's 1 meter by all dimension, and it's recording the thermal infrared radiation that is emitted by the Earth and the atmosphere. And it's orbiting around the Earth. It's doing 14 orbits a day on average. And there are 3 IASIs flying at the moment. One of them just stopped working. It was in fall this year. But for this study, we will exploit basically all the data provided by the Metop A and Metop B satellite. So they are the same IASIs on the 3 Metops. And what this instrument does, it records atmospheric spectra. And it means that the infrared radiation that is emitted by the Earth is traveling across the atmosphere, and throughout its way, it's in fact interacts with different type of molecule. And on each spectra that is recorded by IASI, this is an example of a typical spectra. And we have spectra like this. We have 1.2 millions per day per IASI. And on this spectra, you can see the absorbing signature of each molecule that is present in the atmosphere along the path of the infrared radiation. And so from such a signal, in fact, you can retrieve concentration of trace gases, and you can also retrieve atmospheric profile for important variables like temperature, water vapor, for example. And so basically, since the start, IASI was designed as a versatile instrument. So his first focus is to help to provide accurate forecasts for operational weather forecasting. And here you have an example, in fact, of an analysis that was performed by the Met Office, and it says that using the satellite data, because these data are very accurate and we have a lot of them, in fact, it has the largest impact on any satellite for any single instrument to provide a better forecast, in fact. And the second usefulness of IASI is to derive atmospheric concentration for trace gases. And here you see the list of species that have been already retrieved from the IASI mission. And there are a lot of them. We have more 30 species. So maybe some of you remember that I gave seminars in the past in the same room here, and I was talking about ammonia, carbon monoxide, and so on. And this time we will not at all speak about atmospheric gases. Sarah will talk about a bit of ozone, but that's it. And basically, it was really found that this mission is great to derive atmospheric concentration for trace gas. We have developed very nice retrieval algorithm for each of them. And just to give you a glimpse of the possibility, the initial list of molecules that was supposed to be measured by IASI is provided in blue. And in fact, we have derived much more, in particular if we watch at some events like large fires or volcanic eruption, or air quality, large events of air pollution, for example. And here what we will present this time is in fact a bit of the best we can do for both. It means the algorithm that we have developed for the trace gases helped us a lot, in fact, to understand what we can really see with extract from the spectra. And we will use the same channel that they are using for operational meteorology, but we will do climate research. So we will focus on deriving flux and temperature using updated algorithm, in fact. And in fact, I started to think about it when I was here at NCAR, it's very good for me to come here because aside of working with the great MOPI team, I can also have a clearer brain to think and to be away from home where we have a lot of commitments. And so I thought, okay, this is the map, the typical map that you can derive with IASI for a month. It's just drawing surface temperature, you see that. And what can we see, in fact, if we use the same type of data, but during the whole IASI record? Because the first IASI was launched in 2006, and we will have IASI and its successor, which is called IASI NG, who will fly it until more than 2040. So we will have at the end a record of more than 35 years of consistent data. IASI is very consistent over time. That's the way it's designed, in fact. And so I wrote this proposal, and luckily for me, it was selected, called IASI Flux and Temperature. And in Europe, we have the opportunity to have these ERC proposals, and it's great because it gives you a lot of freedom of doing what you want. You can pay people with that and so on. And if you remember, in 2016, back then, it was this hiatus story. So people were saying, okay, this is like no increase in temperature for the last few years, and they couldn't really explain why. And so at the time, I thought, okay, but with IASI, for example, with a single same instrument, we possibly could observe any change in temperature over a few years. But we were not sure at the time, and in fact, as you will see, it's pretty easy to do even with a single instrument, in fact. So, okay, this seminar will be divided in three small parts, and we will just give you a glimpse of what we can do, of course, because in the interest of time, will not be long for each part. So I start with the radiative fluxes. Okay, the challenging part so I had this, like I say, my treasury is the IASI data. We have a lot of them, but we know how we really know how they mean, what is inside this data. We have been looking at all channels where we can derive from it. The problem is the consistency from the start up to now. And of course, like any new instrument, EUMETSAT at the beginning was making some fine-tuning about different stuff that would affect some of the pixels and so on. So the first thing at the start of this project was to use a consistent data set for radiance temperature. So that we call that our level 1C data. We need them to be fully consistent from the start up to now. So they reprocessed, in fact, 10 years of data so that it's consistent for all the data, including what we have now. And so for that, the device that you see on the right-hand side here, these are disks, in fact, that physical disk that we had to, that were transported from Germany, from Darmstadt in Germany up to our lab. And that was 120 kilo. It didn't even fit in the elevator. So we had really issues, in fact, to get this data. But when it's done, we have this great data set that is fully consistent from the start of the mission up to now. And then we hire a bunch of people. These guys, in fact, I already was working with them. I wanted to have Sarah back. She was at the MIT at the moment. And so that gave me the possibility to pay people, and they were more in the way. So to work on, so everything that we will show today has been obtained also with these guys. So trends in outgoing long-range radiative. So that outgoing long-range radiative radiation, in fact, it's basically the infrared radiation that is escaping from the atmosphere to the space. This is the red square that you see on this iconic plot. And in fact, with IASI, we don't have the whole spectral range, but almost. And up to now, in fact, it's basically other instruments, like, for example, GERB, CRS, for example, those are broadband instruments, so they provide the integrated OLR, in fact, and so you cannot discriminate exactly how this OLR is changing with the wavelengths. And what is great about IASI and also other infrared satellite missions like CRIS or EARTH, for example, is there are hyperspectral sounders. And so you can really discriminate when you look at different wave numbers, how the radiation is changing with the wave numbers and with the time, of course. And that's what we did for IASI. The advantage of IASI, it has two. It has no gaps, in fact. The absorption spectral range, even if it doesn't cover everything from 0 to, say, 3,000 centimeters minus 1, there is no gap. EARTH and CRIS have gaps where, at some spectral range, for example, but here we have no gaps. But basically, all the major trace gases absorbing, all the climate gases, in fact, are absorbing after 600 centimeters minus 1. And so mostly what is before is water vapor. As we have this water vapor band with the new 2 absorption that makes a strong absorption within the IASI spectral range, we can guess, in fact, the other parts that is missing. And so the first thing that I will show you is how this evolved with time, in fact, accumulating more than 10 years of IASI data. For that, there's something tricky to do. What we observe from space is that IASI is providing a single view, so it's always the same angle that when the instrument is looking at a specific scene. Here, what you want to have is like an integrated view, what is escaping to space, in fact. And you need to integrate that over 2 angles, in fact. And so this is a bit tricky to do, in fact, and for that we made tons of simulation, and we have tables to convert, in fact, what we observe with IASI into this OLR signal, and we did that. It took at least a year, more than that even. It's the work of Simon Whitburn, in fact, that did that at ULB. And now he has this table well set. He did thousands and thousands of simulation using the CAMS data, Copernicus CAMS data, that are quite realistic. And now that we have this tool ready, we can try to do trends. This is a reminder of what the IASI spectral looks like. And so on this, you can see several stuff. You can see here what, CO2 absorption. Then this area is used, in fact, to retrieve surface data, because this is directly the skin temperature. You don't see my mouse. Okay, that's not very convenient. Okay. Do you have okay. Okay, it doesn't matter. Okay, I'll show you that directly. So near 800, it's basically absorption of CO2. Then there are absorption in the atmospheric window. Then there is ozone that is also changing. Then the atmospheric window again. Then water vapor. Then CO2 again. And then we will look in detail. So on the weight plot here is wave number versus latitude. And we will look at several areas, and we will, in fact, put that on a map and to see what is increasing in terms of OLR and what is decreasing, in fact, and where does it come from. Okay, and here, on this map, we'll first focus, in fact, on what we call the atmospheric window, and then here you have basically every phenomena that is occurring at the surface, and it will impact temperature, surface temperature. So Sarah will talk a lot about that. But here, what you can see, in fact, remember that we have a record of a bit more than 10 years. During these 10 years, there were 2 La Nina events and 1 very strong El Nino in 2015 and 16. And what you see here, I'll move on. What you see here, it's basically linked to this El Nino events, and we have the Pacific decadal oscillation, we have the Antarctic dipole. Both of them are strongly linked to El Nino. We have this North Atlantic warming hole. This is, in fact, the ice melting from Greenland, and that is also affecting the AMOC, the strong movement of water that occurs in this area of the globe, for example. That you can look at short term, for example, with the IASI data. You can also look at water vapor channels, and here you also see the strong impact of El Nino, for example. Here you see on the left-hand side the water vapor, the right side it's a temperature at 500 hectopascal. If you look at CO2 channels, I'm going backwards a bit here, sorry. CO2 channels, it's a very high, it's near 600 centimeters -1. There's one CO2 band over there, and at the other, near 2300, there is another CO2 band that is also important. And if you look at that, you can see, in fact, that the increase of CO2 means more absorption of the infrared radiation near the surface in the troposphere, and then you have less OLR in this spectral range going out to space, in fact, because of this increase of CO2. If you look closely, in fact, in this atmospheric spectral region, there's also tons of little absorbers, like CFC, for example. CFC are like 11 and 12. Those were the CFC that were, in fact, forbidden to emit linked to the Montreal Protocol. And so they are decreasing, and it means more OLR radiation in the spectral range where they're absorbed, in fact. And it's the contrary for SF6. SF6 is increasing, and so it means less absorption in terms of OLR. Here you have the spectra and the trends over all these, with all these molecules flagged, in fact. So those are only a few examples. If you wanted to know more, there's a paper where Simon is gathering all this. Okay, so we did the same, this was OLR, we did the same just for temperature, in fact, and that's the work of Marie Bouillon, who was a PhD until recently. So IASI is, as I said from the beginning, IASI was supposed to provide information for the weather forecasting, and those guys, they are assimilating radiances. EUMETSAT is also delivering a product, temperature product, but the issue is that temperature product is that with the time, it has changed a lot. So there were no consistent temperature retrieval from the start of the mission until now. But they were improving the algorithm over time, in fact. And this is what you see on this plot. If you look, for example, we did that for two areas of the globe. The red line is representative of the northern hemisphere. The blue lines are representative of the southern hemisphere. And the plot shows, in fact, the comparison between the temperature as retrieved from IASI at an altitude of 500 hectopascal, which is about 6 kilometers, and it compares it to ERA 5, so the ISMWF reanalysis. And so, as you can see, the record is varying with time. At the end, we have a very good agreement. This is because the retrieval algorithm of temperature was improved over time. And it's not only the temperature. I didn't mention that up to now, but for example, we have an issue with the clouds in general. We don't see across the clouds. And so we need a very good cloud filtering to process only the clear data set. And at the beginning, as you see, there were several changes, both in the retrieval algorithm of temperature and also in the cloud coverage, how to discriminate a cloud scene from a non-cloudy scene. And so there are ups and downs, and you see the record is not consistent, so we cannot, in fact, analyze the temperature records since the start up to now. We couldn't. And to fix that, in fact, we have developed our own algorithm, and this is the work of Marie when she was a PhD. She did an ozone layer network, and she trained it with observation, and it's pretty easy. In fact, the input is well-selected radiance line that are sensitive, in fact, to the temperature at different altitude. She chose a set of channels that are indicated here with the pink lines. And she trained the network, in fact, to recognize, in fact, the radiance and to associate them to temperature profile. And for that, we use the CO2 bands, as CO2 is very stable in concentration. And there's an input, in fact, to adjust the change of CO2 over time, because, of course, it's changing. But we can just tune these parameters because it's changing very slowly. in fact. And then she trained a network, she validated it with real data and so on, and now she has a consistent, she has a tool to derive consistent temperature throughout different altitude and for the whole IASI record, in fact. And this is what it gives for trends, in fact. So this is basically what we expect. So the troposphere is warming, the stratosphere is colder than before. But remember that it's only this is between 2008 and 2020. So we are still very sensitive, in fact, to internal variations. So the strong El Nino phenomena, and so they all have an impact here. Basically, what you see so in general, in fact, there is an increase that is higher at the pole than it is, at least at low altitude, that it is at mid-latitude and in the equator, with an exception when you go quite high in altitude. The cooling is obvious when you go to the stratosphere, with the exception of two areas. And in fact, the first cooling here, Sarah will come back to that, it's linked to a very strong, in fact, sudden stratospheric warming that occurred in 2019, and that has an impact, in fact, over this. It was so strong, in fact, that you see it on the trends. And the other high, the other increase in temperature per decade, it's linked with the ozone recovery, in fact, that you see here in these trends. And we can compare that directly to what is provided by ERA 5. And as you can see, there is a really good match between the two, in fact. Forgot to say that the dark gray lines are the areas where the trend is not significant. But I think that was great to obtain that with a single instrument, in fact. This is the general trend, but we can also have a look at more specific events. I'll show you two of them. It's quite funny to do. So each time that we have an increase of temperature somewhere on the globe, we can show it with IASI. And this first one is the high temperature that were observed both on the west coast of America and also in Central Europe. That was last year, if you remember, that there were huge fires in California, for example. And if you look at here on the left-hand side, in fact, it's the average over the whole IASI period, so same period of time, so June. And you see the average, and you see the maximum and minimum temperature. And what you can see in June 2021, during a full month, the temperature was exceeding the maximum temperature of the whole period before. So that was for last year. And this year, we had a very large increase of temperature in June. There's one other coming now this week. And the temperature plume that you definitely see moving across Europe, traveling across France, and going to Germany. And again, here you see a very high temperature as compared to the mean and minimum and maximum values. And last but not least, do you remember that eruption of Hunga-Tonga that occurred in January this year? And when I saw the fact that there were impact pressure level at the surface, I said, oh, what can we look with IASI? And this is on this small animation. In fact, you really see the system of waves that were spreading away from the volcano. And that was huge. We never saw anything similar to that with IASI. This is an integration between those are the temperature change between 2 and 30 hectopascal. In fact, you see basically the same stuff with Chris and airs. And that's the very first time we see that. So it means that the eruption was so large that, in fact, it perturbed all the atmosphere, and the waves, in fact, were eating. You see the eating of the atmosphere going away from the eruption. And so that was great because we could contribute, in fact, to that paper which appeared 2 weeks ago in Nature. And these guys from the Bath University, they collected all the data they could find from the surface up to the ionosphere. and try to analyze the speed of the wave, in fact. And IASI with Chris and Ers, in fact, together, they were able, in fact, to measure the speed of the wave in the stratosphere, and that's really a great work. Okay, Sarah, it's your turn.
So while Marie was doing her retrievals of temperatures, a rare event happened in Antarctica in 2019, which was a sudden stratospheric warming. What happened is that, as you know, we can measure ozone distribution from IASI since its launch, and this is what we do every year when, over the ozone hole period, we can monitor the evolution of the total ozone column. And if you look on this plot, you can see how 2019 was particularly different in a way that the ozone total columns were quite high. That year was really special because even when we compare the average, this is the ozone hole area from the Ozone Watch website, we can see how 2019 was exceptional because it was twice and more lower, the ozone hole was twice as and more lower than the 10-year average, 11-year average that you see here. And that was particularly extreme in a sense because some of the studies talked about no ozone hole in 2019 at all. This was caused by a sudden stratospheric warming, which is quite common in the northern hemisphere. It is due to planetary waves that break the polar jet. The polar jet is quite stable in Antarctica, but it is not as stable in the northern hemisphere, so we have it more usually in winter in the northern hemisphere. And what happens when the polar jet, when there's a breaking of this, the jet stream, we have this exchange of air between the stratosphere and the troposphere, and then the temperature can rise very suddenly over the course of a few days. Hence the term that we say it's a sudden stratospheric warming. Over Antarctica, the polar vortex is very stable because Antarctica is surrounded by the ocean. We don't have any mountains that might provide these planetary waves, so it doesn't happen. The only two events recorded since the discovery of the ozone hole were in 2002 and 2019, so we're lucky to be able to check what's happening with the IASI data in 2019. So I used the geopotential height as a measure of the polar vortex stability. Typically, the polar vortex is really concentrated over the poles. So a typical polar vortex is what you see on the first slide, the beginning of August 2019 at 10 hectopascal. But then you see how the winds moved a little bit, the polar vortex till the Andes. This meant that the wind hit the Andes, which provided a planetary wave that went to the stratosphere and affected the polar vortex, as you see by mid-September. The date is written on top. We can look at what this provided in terms of effect on temperature on the upper panel and on the anomaly of the temperature on the lower panel. So on the x-axis is the date, on the y-axis the altitude, the pressure levels. And we can see, for example, at the beginning of August, it was a typical year, a typical winter. The temperature anomalies are close to zero, everything is normal. And then by the beginning of September, things started to change. We can see how we have a sudden increase in temperature from one day to the other directly. And this has propagated over the atmosphere and then reached a maxima around the mid of September with really shifting of this polar vortex. In our lab, we have the people working on the French Antarctic station, Dumont d'Urville, and we were able to compare both the IASI data over the 60-90, so we are really over the whole of the poles with one station at Dumont d'Urville, and that was really nice because we can see exactly the same temporal distribution. These are our balloon sound measurements, so they launch balloons every day, and then the burst altitude is where we stop having the measurement. The numbers are a little bit higher just because it's more concentrated, because the IASI data is an average and Dumont d'Urville is just one station. But nevertheless, we see that we have very similar temporal distribution. At Dumont d'Urville, we also have measurements of PSC. We measure the scattering ratio. And the study, we did nitric acid, we did T minus T nat as a measure of PSC formation. And this year in particular, there were no polar stratospheric cloud formation, suggesting very little depletion of ozone. So just to summarize, we have a temperature anomaly reaching 30 degrees that year, which is quite rare. And this affected really the ozone distribution in Antarctica, leading to an enhancement up to 100 DU. And on average, actually, on September, the mid of September, we had an increase of more than 35% than the 11-year average of IASI data. And the results of these papers were published in JRL. So the last task of the ERC was to derive a surface temperature product from IASI. So I'm going to talk about surface or skin, and it is also called in the literature land surface temperature when it's only over land, or sea surface temperature when it's over the sea. In any case, it is a measure of the heat that is coming out of the land. It is important because it's a climate essential variable. It is affected both by land use and both by atmospheric changes and interactions between land and the atmosphere. So it is an important variable that we can have from IASI, especially in regions on the spectrum that are transparent. So when we don't have anything between the instrument and land, we can have directly the infrared radiation coming out of the surface, which is the thermal energy, which is the skin temperature. So the first part of this was to calculate and provide a clear sky product, which was done by a very minute selection of the IASI channels that are very sensitive to T-skin. And this was done actually on the left side of the ozone band, where the atmosphere was, according to our test, was the most transparent over different atmospheres. We trained those in a neural network and colocalized in space and time with ER5 and validated it in a paper to get these products that are monthly temperature product over day and night. You can see when we don't have, since it's a clear sky product, so over the equator sometimes we have missing data, but nevertheless we have this consistent skin temperature product from IASI that we were looking to exploit. So there are already T-skin products from infrared measurements, and one of which is the one on AIRS. These two products are quite interesting because AIRS and IASI have similar spectral resolution, ground footprint, but they have different crossing time, they are on different orbits, and different retrieval algorithms. So in a sense, we have two products that are completely independent, and this provides really a nice way to see how they compare or why would they be different. So IASI on Metop has a crossing time around 9:30 a.m., 9 p.m., and AIRS on Aqua, it's on 1:30 a.m. and p.m. So the first thing that I've done is to compare the temperature of IASI and AIRS. And since AIRS has a crossing time later, so the temperature at 9:30 a.m. from IASI are colder than those from AIRS. So on top is the difference during the day, and on night, on the bottom, the difference between night. And we can see how it's really clearly dependent on the crossing time. So the temperature, for example, at night at 9:30 p.m. is from IASI is warmer than at 1:30 a.m. in the morning from AIRS. You notice that there is off the coast of Antarctica a region that is a bit funny. This is because AIRS has a retrieval error over the freezing ocean, and it is also you can also see it in parts of the northern hemisphere. So this is just to sum up a little bit the box plot of the differences. The difference over the ocean in blue day or night is close to zero because of the large heat capacity of water. Water takes time to heat and cold, whereas land is highly dependent on solar energy. It cools down and heats up much faster, and the differences are positive during the day and negative during the night. So the natural thing was to look at the trends, both from IASI and AIRS. So top panel IASI, lower panel AIRS, day and night on left and right, and the trends are on the same color bar. And this was really nice to see because we have really nice correspondence. Again, they're both different retrieval. They have similar sounding method. They're both in the infrared, etc., but they have different retrieval, so they're completely independent. And we can see that they have quite similar trends over the globe. We can see that for AIRS, the colors are a little bit more saturated, suggesting maybe that the climate change signature depends on the time of the day. We see how over Russia and Siberia and also Alaska, we have higher trends, probably due to the large fires. And I discussed this in detail in my paper that I just submitted a couple of weeks ago. We had to have a reference for these to say what if we what we're detecting is real or not. This is from GISTAMP, which is the trends near the surface. So it's not at the surface. We are very close to the surface. But assuming this is a trend and assuming that whatever is affecting the surface will affect on the long term near the surface, we should expect similar trends. And this is exactly what we see. This is based on more than 6,000 station measurements, and we can see that actually both, this is on the same. The GISTAMP is only provided day and night for the same time period, and we have actually, at least spatially, the trends are very close. I discussed this in detail with the natural variability or anthropogenic forcing. I talk about it for the sake of time. I will just end up with this. On the x-axis, the area weighted latitude, just not to give a lot of weight for the poles as much as the equator. On the y-axis, the trends, and for the different data set that I use here. This is just to show the complementarity of these different data sets, where, for example, for GISTAMP, we have little to no station in high latitudes, and for this reason, maybe satellite measurements could be a great tool. The satellite measurements aren't perfect. They might have retrieval error, or IASI might have no coverage because of the cloud cover mask hues. But in any case, we can see that they correspond very well, and that these different data sets might have excellent complementarity. When one can fail, the other can support. So to end up, I should just show what I've been doing last week while I was here. What we can do with this product, we can, for example, monitor drought and fire. This is part of a conversation article that Cathy wrote, where we just discussed the anomaly of skin temperature in May and June 2020, where the fires in Siberia in June were as large as Greece, and the CO was used as a tracer for fire activity. And we can see that with the skin temperature, we can actually monitor those changes from day to day, although here we show month to month. So using an oversampling approach, which is averaging the real footprint of a IASI, that is an ellipse with another ellipse, instead of the traditional methods of averaging by taking one by one grid and putting everything at the center of the measurement that we get, we can have higher resolution maps such as those. Those are a 5-year snapshot, and 2008, 2012, day up and night, and then in the middle, the other 5 years, and then in the last one is just 4 years, because I still don't have June, July, August of this year. And you can see, we really need a lot of data for this oversampling approach for work. But nevertheless, I'm going to show you that it can have some nice applications, where if we zoom in over this region, and I'm changing the color bars just to show how we can have, for example, these urban heat island effects that pop up, averaging 5 years of data. You can see all of the small cities, and then in particular, I show here these examples of St. Louis and Louisville, and then just extracting from Google Earth Engine the modest land cover, we can see how IASI data can actually really detect the changes. You can see the tail of in St. Louis, that we can actually see it with the IASI data, and that was nice. Just for the fun of it, I did for Denver too. There's a lot of greenery, and greenery brings a lot of moisture, so lower skin. Nevertheless, we can have a small hotspot. I changed the color bar here. Or also here where we have this arid region, so it pops up with higher temperature because simply we don't have a lot of greenery around inside, so it have higher temperature. What I just want to mention also that it's not only an urban heat island, we have the opposite, the urban cool island effect, which is common for desert cities or cities in arid regions. We have, for example, here the example of the city of Riyadh, where we see that the surrounding of the city of Riyadh for once during the day is hotter. That's because sand, and you can remember the feeling when you walk on the beach in summer, the sun's temperature can be extremely high, and then once you go in the shade, the temperature drops down quite fast. That's because the sun takes up heat very fast and give it up very fast. However, the mosaic of a city might have different land type cover, and so it is actually colder than the sand. During night, the city becomes a typical urban heat island effect, and that's because, again, sand or in the desert during the night is quite cold, and the city traps heat much higher. This led me to a study that I worked with, that I've done earlier this year on the Arabian Peninsula, where I looked at different regions. And the idea is that this Arabian Peninsula is very interesting. On the one hand, it has the largest desert in Asia. On the other hand, it has a large economic and social expansion. It has a desert. It is also very close to the coast, has one of the warmest beaches, and sea temperatures. I'm not going to talk about the region, the upper region, but this is the effect of irrigation. Irrigation decreases the temperature. This is the largest irrigated region in Saudi Arabia, and you can see how from LSD we can actually get an idea on irrigation. So the question is that I was trying to ask is how can we relate hot and humid to the humid heat tolerance? And for that, I calculated the Webber temperature, which is becoming quite the hot term these days as a measure of human comfort and heat stress. When it approaches our body temperature, the body organs cease to function properly because we won't be able to dissipate heat by transpiration. So we can see that already we are hitting very high temperatures today. This was a work that was done already. So what we should know is that the Webber temperature is a nonlinear function of near surface temperature and humidity. And an example here I've done for June 2020. You can see, for example, for a temperature that is 31 degrees, the Webber temperature can move really from 10 to 28. And 28 is actually an uncomfortable heat when the relative humidity goes from very dry to very humid. So the human survivability threshold is around 35 degrees C in a well-ventilated outdoor condition. Focusing on this study, focusing on the Arabian Peninsula, so here we are here. So the cities, the big cities of Dubai and Abu Dhabi, which have a good number of population density, the land surface temperature is lower because of the humidity brought by the coast, although inside it's much higher. However, the Webber temperature, I forgot to mention, it's calculated from ERA 5 because we cannot have it from IASI, is much larger. This is an average, although locally it could be much higher. This means also that we are already in a stage where it's really thermally uncomfortable in these regions. And what was interesting to see in the study in particular is that the early evening heat stress is higher than the morning heat stress. And at 9:30 p.m. in Dubai, for example, this is actually when people tend to go out or do their sports or whatever. However, the thermal comfort is there's a lot of more of heat stress at night and early evening than during the day. As I've already shown, the urban heat island during night and urban cool island over the day. However, the web belt temperature, we are 500 kilometers away from the coast, is much lower. So the heat stress in Boulder, for example, or Riyadh is much lower than it would be on a humid coastal city. And this, I've done this over different scenarios, mid-century and end-century, good and bad, to just show that the human survivability in this region will really be threatened under any scenario, actually, and more so under the SSP 585. And the other major conclusion that I didn't talk about here for the sake of time is that irrigation should be probably included in all of the climate projection, not only a few of them, because irrigation, especially in cities, bring a lot of humidity, especially in coastal cities. And then, maybe it should be taken into consideration when to irrigate, the type of species and plants to be taken into account. And the result of this study are published in ERL. So all of the slides that we showed today are different products that you can check and retrieve from the IASI Flux and Temperature website, where you have you have different resources, all of the products. We also have a sea surface temperature product that we developed that we didn't get the chance to talk about. And much more. You can learn a lot about IASI, about temperature and OLRs from this website. Voilà. Thank you.
Thank you, Cathy and Sarah. Let's see if we have some questions from the room or from the people online.
Very nice talk, thank you. So Cathy, you derive, the discussion you had was using cloud-free data. Does that introduce a bias in terms of the trends that you see?
Okay, that's a good question. So we have spent a lot of time on that, and I think it introduces a bias. And to study that, in fact, we started to derive trends in the cloud coverage. So that's a side study that I didn't show in the interest of time. But yes, there's a bias related to that, I'm sure, yeah.
Well, now I'm curious, what are the trends in the clouds?
So, yeah, the paper is submitted. Yeah, okay, so, yeah, I should look back at the paper. The problem is that we don't have a very long record. Yeah, so there's no real accurate trend over the 10 years, but at least now we have we reprocess, in fact, all the data sets for only the cloudy data. So we have the similar study as I've shown here, with only cloudy data. And so that's like two parallel studies, one with cloud-free data, cloudy data. And so we are still in the process of trying to understand, but there's no clear trends over the 15 years. It's too short, I think.
I'm personally curious to hear if and what new things are in the new satellites that have been launched, if you know. So
do you mean the new
the
follow-on?
IASI NG, for example.
Okay, so this is it. Oh, sorry, where is it? Okay, here. IASI NG, the difference is that it has the same pixel size as IASI, so no more chance to see across the cloud because the pixel size stays the same. But it has twice the signal to noise, so we will see deeper in the atmosphere. And also twice the spectral resolution, which means that we should be able to see more resolved profile. For example, for CO at the moment, we have at most 2 levels of information, and we might have 3 with IASI. The simulation show that. So we should have more accurate products. I'm not sure if we would be able to retrieve more species, for example, but for example, for temperature, we will have like more levels that are independent from one from the others, in fact. So, but the tricky thing is that it's called IASI, but it's a totally different instrument. It's not even the same industry that is designing it. So at one point I wanted to change the name, but the agency they didn't want because they say, oh, let's build on the heritage of IASI. But that will be a major stress when IASI on Metop C is done and we have launched the first IASI because hopefully we will have an overlap between these two guys. There's one more stress is that the first IASI is supposed to be launched by a Soyuz launcher. And as you know, that will not happen. So they're trying to jump it onto an Arabian launchers, but everybody that was supposed to be launched by Soyuz is trying to do the same. So I think the major stress is to have no overlap over the last IASI and the new IASI. But the second IASI is still working. And the first one, in fact, was decommissioned because of the whole Metop platform, but it was still functioning. So 15 years after the first launch, the first one was still functioning. So my hope is that the last one will still function when the first IASI is launched. Okay.
So this is a great amount of information. I like the temperature, but have you thought about water vapor? There's a whole parallel set of questions on water vapor.
That's a very good question. So with Sarah, we are discussing that. We say the next thing to look at is water vapor, because I think there's tons of stuff we can do by looking at the same time as temperature and water vapor. Yeah. I know. There's some stuff that are not exploited yet, and that's one of the stuff we need to look at.
Yeah, a similar question is, does IASI have a VPD, a vapor pressure deficit product?
No, I was not even aware of this acronym, so
okay, yeah,
the answer is no, I'm sure not.
So AIRS does, and it's used for drought monitoring and then fire prediction. And you didn't really get to that, Sarah, with your drought monitoring, but but I can give you a good paper to read.
We need to look at that.
Yeah, that's like something that's being used to show that night fires are no longer suppressing. Or the nighttime is no longer suppressing fires the way it used to because VPD is.
Yeah, okay.
Anyway.
I didn't even know the acronym, so that's good to know.
Okay, it looks like we don't have questions from the online folks. We have one more question in the room.
So a question for Sarah. When you're working out these heat island effects, it's going to be, you have a strong dependence on your assumed emissivity before you start. How confident are you that in your emissivity a priori before you start trying to work out what the deficit is?
So in the neural network, I use 100 IASI channels and then emissivity over each of the channels. So over land, I use emissivity as input to account for land cover changes due to emissivity effect. So this is included inside the product indirectly.
I have also a curiosity about the neural network you chose. It looks like you used it to basically select data. Is that right?
No, we already selected the IASI channels. We use it to predict what would be, as a model to tell us what would be the temperature.
So can you repeat what was the input and the output of
So for the... it depends for what of the studies, but for the skin temperature, I had 2 neural networks, one over land and one over sea. Over the sea, I just took the raw IASI channels and then trained that. So IASI channels input and output was ERA5, and that was enough. And then over land, because we need an idea about the emissivity because it changes with land cover type, I used IASI channels and then emissivity at each of the IASI channels. So there were 100 channels, 100 emissivities, and then output was ERA5 temperature.
Thanks.
Sure.
Let's thank Cathy and Sarah once again.
Thank you for being here.